record. Okay,
Thank you.
thank you. Okay, what's your question? Your first question.
1.1, number 6. Is it in that it's the center of a group G is the set Z of G equals X, an element of G, such that XG equals GX for all G in G.
Okay. And is there a
We
question?
have to prove that it is a subgroup.
Okay. So,
If we know that X is in G, isn't that enough to just say it's a subgroup?
well, so the center of a group G is the set Z of G. It's Z because in German, where everything started, the word for center is centrum, which starts with a Z. It's everything in the group that commutes with everything else. XG equals GX for all G in G. So Z of G is contained in G. And usually, so if G is a non-abelian group, then Z of G is not equal to the whole group. So it's a proper subset. And you do have to prove that it's a subgroup.
So that it's a proper subgroup.
Well, so if G is not abelian, then the center is a proper subset of G. So it's not obviously a group. It requires a proof. So proof that Z of G is a subgroup of G. So let's see, what do we have to prove? So if X and Y are in Z of G, then what can we say? For all G in the group, if we take XY times G, so we're just using associativity, this is X times YG, but Y is in the center. So YG is the same as GY. And again, by associativity, this is XG times Y. So from here to here is because Y is in the center. And this is associativity. And this is associativity. And then this is the same as GX times Y because X is in the center. And then this is the same as G times XY. And this is by associativity. So XY times G is G times XY. So XY is also in the center, which means the center is closed under multiplication. So that's the first of the 3 conditions for a subset to be a subgroup. Second, if you take the identity element E times G is G, is the same as G times E for all G in the group. That's the meaning of an identity. So the identity is in the center. And third, we have to show that if X is in the center, then X inverse is in the center. That's the final condition that you have to show for a subset to be a subgroup. So what can we say? So for all G in the group, we know that XG equals GX. So if you multiply on the left by X inverse XG equals X inverse GX. I'm just taking this element and multiplying on the left by X inverse. And let's say I also multiply on the right by X. Of course, X inverse X, that's just G. So GX is X inverse, sorry, I want to multiply on the right by let me do this in 2 steps again. So let me multiply on the left by x inverse. I get x inverse g. I get x inverse xg equals x inverse gx. I just multiplied this element on the left by x inverse. And let me also multiply it on the right by x inverse, x inverse, x inverse. And you see what happens. X inverse x is the identity, that cancels. X inverse x is the identity, that cancels. So what we have is gx inverse equals x inverse g for all g. So x inverse is also in the center. And we're done. So if you take the center of a group, it's closed under multiplication. It contains the identity element, and it contains the inverse of each of its elements. That's the proof.
Thank you.
Professor, can you do, from the group theory notes, section 1.5, number 10, please? 1.5, number 10, thank you.
So what is, see, I keep improving my notes in various times. What does your number 10 say?
Okay, it says, construct a subgroup H of S3 and an isomorphism from Z mod 3Z to H.
Okay. So S3 is the symmetric group.
Can you move the page down? Thank you.
So S3 is the symmetric group, which is the permutations of the numbers 1, 2, and 3. And you want me to take the cyclic group? Is that the question?
It says construct a subgroup H of S3 and an isomorphism from Z mod 3Z to H.
Okay. So what does S3 look like? You have the identity, you have the 3 cycle 1, 2, 3, and its inverse, which is the 3 cycle 1, 3, 2. And you have the transpositions 2, 3, 1, 3, and 1, 2. Those are the 6 elements of the symmetric group. I usually call this sigma. This is sigma squared, which is the same as sigma inverse. And this is tau 1, tau 2, and tau 3. So these are the 6 permutations in the symmetric group. And there's only one subgroup of order 3. I just take H to consist of the identity sigma and sigma squared contained in S3. So this is, in fact, this is a multiplicative cyclic group of order 3. And I can define a function f from Z mod 3Z into H by f of the congruence class x plus 3Z equals sigma to the x. And so first of all, so this is a function, right? I mean, for every congruence class, x plus 3z, I let it be the permutation sigma to the x. The identity is like sigma to the 0. And sigma cubed is the identity. So if x is congruent to y mod 3, what does that mean? Then x is y plus some multiple of 3. So sigma to the x is sigma to the y plus 3k. This is sigma to the y, sigma to the 3k, which is sigma cubed to the k. This is the identity. This is sigma to the y. So in this map, this is well defined because every element in this congruence class gets mapped to the same permutation in H. So this is my function. This is a well-defined function because sigma has order 3. So f of 3z is the identity, f of 1 plus 3z is sigma, and f of 2 plus 3z is sigma squared. So this function is one-to-one and onto. Why is it a homomorphism? So let's just check. So need to prove f is a homomorphism.
Actually, it said an isomorphism.
So an isomorphism is a homomorphism that's one-to-one and onto.
Yes.
So f is one-to-one and onto. So to prove it's an isomorphism, you just have to prove it's a homomorphism. So what does that mean? It means that if I take f of the sum of two congruence classes, x plus three z plus y plus 3z, that's f of x plus 3z times f of y plus 3z. Right? In this group, the operation is addition. This is an additive group. H and S3 are multiplicative groups. So here I have a plus sign because all I can do to congruence classes in this additive group is add them. And here I have a times sign, so all I can do with S3 is multiply. So this is what we need to show. Must show. So f of x plus 3z plus y plus 3z. This is just the congruence class x plus y plus 3z. So that gets mapped to sigma to the power x plus y, which is by just rules of exponents. This is sigma to the x, sigma to the y. Sigma to the x is f of x plus 3z, and sigma to the y is f of y plus 3z. So this is true. End of proof.
Can we do number 7 of that same section, 1.5?
So can you read that problem?
There are 3 parts to it. The first is let tau equal A1 to AK be a K cycle in Sn, and let sigma, an element of Sn, be an element of Sn. Prove that sigma tau sigma inverse is the K cycle sigma A1, sigma A2 to sigma AK.
Oh, okay. So this is a special case of the following general statement. So suppose we take tau to be any permutation in Sn and sigma to be a permutation in Sn. So let's write tau in the standard form, 1, 2, 3 up to n, and this goes to tau of 1, 2 goes to tau of 2, n goes to tau of n. That's just the standard way you write a permutation. And let's consider sigma tau sigma inverse. So this is a permutation in Sn, okay? How does this permutation behave? What does it do? So every integer in the set from 1 to n, or I can just say the set of integers from 1 to n, is the same as the set of integers, sigma of 1, sigma of 2, up to sigma of n, because sigma is a permutation. So it just rearranges the numbers, but in a set doesn't have an ordering. A set is just a set of its elements. So every integer can be written in this form. So let's compute sigma tau sigma inverse applied to the number sigma of k. So what is that? That's sigma tau sigma inverse sigma of k. Well, sigma inverse sigma of k, this is just k. So this is equal to sigma tau of k. So the permutation sigma tau sigma inverse, it sends the sigma of k to sigma of tau of k. So, sorry, yeah, that's right. So sigma of k goes to sigma of tau of k. So suppose I have the cycle tau is what, A1, A2 up to A sub k? Is that what I said?
Yes.
Okay. So what does this mean? This means that tau of AI is AI plus 1 for I going from 1 up to k minus 1, and tau of AK comes around to being A1. So what is, okay, so sigma tau sigma inverse applied to sigma of some AI is sigma of tau of AI. So see, how do I want to say this?
So if we have tau of AI would go to AI plus 1. So we have equals sigma of AI plus 1.
So the idea is to show what? We want to show that sigma tau sigma inverse is a cycle which sends sigma tau of A1 goes to sigma tau of A2. Well, that's exactly what this says. Goes to sigma tau of AK of AK. How did I state the problem? Because I don't have the notes here.
Prove that sigma tau sigma inverse is the K cycle, sigma A1, sigma A2 to sigma AK.
Okay, so if I apply, let me write this down freshly over here. Sigma A1, A2 up to A sub k, sigma inverse equals sigma of A1, sigma of A2 up to sigma of A sub k. That this K cycle gets sent to this K cycle. So let me just give this a slightly, let me just call this rho for a second. So what is rho of sigma of A1? So that's sigma A1 up to AK sigma inverse applied to sigma of A1. Sigma inverse sigma, well, they cancel. So this is sigma of A1 up to AK applied to A1. A1 up to AK apply A1. This sends A1 to A2. So this is sigma of A1. Ah, perfect. Well, we did it. So suppose we take any AI and we look at this permutation applied to sigma of AI. So this is sigma, the cycle, sigma inverse, sigma of AI. This is the identity. So this is just equal to AI. AI gets sent to AI plus 1. So this permutation, sends sigma of AI to sigma of AI plus 1 for I going from 1 up to K minus 1, and sigma of AK gets sent back to sigma of A1. So this is all we have to do. This is the calculation, if you like. You have a K cycle, and you multiply it on the left by sigma and the right by sigma inverse. That's called conjugation. You conjugate this K cycle by the permutation sigma. And you get another, this sends this K cycle to another K cycle, namely the K cycle that sends sigma A1 to sigma A2, sigma A2 to sigma A3, and so forth. That's what it is.
Professor?
So just one second.
Sure.
Are there any questions about this?
The beginning part that you did was just to gain a better understanding, but this is all you had to do to prove it,
This is
right?
all you have to do. I was trying to show how it follows from a somewhat more general fact, but it's easier to do it like this. So a cycle is a very special kind of permutation. And I started to try to prove what the general statement would be for an arbitrary permutation, but the problem only asks about cycles, and for cycles, the proof is easier. It's just these couple of lines.
Can we also do part B and C?
If you tell me what they are, I will be happy to do them.
Let sigma and tau be elements of Sn. Prove that if tau is a product of R pairwise disjoint cycles of length K1 to Kr respectively, where K1 plus all the way up to Kr is n, then sigma tau sigma inverse is also the product of R pairwise disjoint cycles of lengths K1 to Kr.
Right, okay. So read the problem one more time.
Let sigma and tau be in Sn.
Okay.
Prove that if tau is the product of R pairwise disjoint cycles.
Okay, all right, stop. That's enough. So I just needed to know which was sigma and which was tau in this problem. So tau is a product of cycles. Let's say A1, A2 up to A sub K1. So this is cycle of length K1. And say B1, B2 up to BK2. And so forth up to C1, C2 up to CK sub R. So we have tau is a product of R pairwise disjoint cycles. So the numbers in these cycles are all different. None of these is any of these is any of these, and so forth. And the sum K1 plus K2 up to K sub R is equal to N. So we've decomposed tau into a product of pairwise disjoint cycles. And then I want to look at sigma tau sigma inverse. What is that? That's sigma, and this is tau, A1 up to A sub K1, B1 up to B sub K2, and so on, C1, the cycle C1 up to C sub K sub R, sigma inverse. So all I've done is replace tau by this expression for tau. And then I can always multiply by the identity, which is the same as sigma inverse sigma. So I'm going to put in a sigma inverse sigma, sigma inverse sigma, sigma inverse sigma. I do this for, I put this sigma inverse sigma, the identity, in the middle to separate every one of the R cycles here. So, but what is this? This is just a cycle conjugated by sigma. So this is sigma of A1, sigma of A2, up to sigma of A sub K1. It's that cycle. This is sigma of B1 goes to sigma of B2, goes to sigma of B sub K2. Up to the last, which is the cycle, sigma of C1, sigma of C2, up to sigma of CK sub R. What do I have here? This
to all
is,
the sigma inverses.
excuse me?
What happened to all the sigma inverses?
Well, sigma times this times sigma inverse is equal to that. That's what we just proved here, right? That was part A. If you take a cycle and conjugate it by sigma, you get another cycle which looks like this. Right, sigma times this times sigma inverse is this cycle. That's exactly what we're using here. And this is a cycle of length K1. This is a cycle of length K2 up to a cycle of length K sub R. So I have R cycles of exactly the same lengths as in the permutation tau I started with. And because sigma is a permutation and the A's and the B's and the C's are pairwise distinct, the same is true for their images under sigma. So this is a decomposition of this permutation into R pairwise disjoint cycles of exactly the same lengths as the original decomposition of tau. That's the proof. Well, that's a proof at least.
And then part C says, let tau 1 and tau 2 be permutations in Sn. Prove that tau 1 and tau 2 are conjugate if and only if for some positive integer r, there is a partition of n into r parts, where n is equal to the sum of k1 to kr, such that both tau 1 and tau 2 can be written as the product of r pairwise disjoint cycles k1 to kr.
So I think what that says is the following. So suppose tau 1 is a product of disjoint cycles, A1, A2, up to A sub K1, B1, B2, up to B sub K2, up to C1, C2, up to C sub K sub R. So here tau 1 is a product of R disjoint cycles of lengths K1, K2, and so forth, up to K sub R. And tau 2 is also a product of disjoint cycles of exactly the same lengths. I'll call it A1 prime, A2 prime, up to A prime sub K1, B1 prime up to BK sub 2 prime, and so forth, up to C1 prime, up to CK sub R prime. So I have two permutations, and they have the same kind of decompositions into cycles. So this is product of R cycles of these lengths. This is a product of R different cycles, but of the same lengths. So if I define a permutation sigma in Sn by sigma of A1 equals A1 prime, sigma of A2 equals A2 prime, and so forth, sigma of A sub K1 equals A sub K sub 1 prime, sigma of V1 equals V sub 1 prime, and so forth, sigma of C1 equals C sub 1 prime. So I'm defining a permutation that sends A1 to A1 prime, A2 to A2 prime. I'm just pairing off the elements like this, and that is a permutation. It's a one-to-one and onto mapping from N to Sn to itself. And by what we just proved in part B, sigma tau 1 sigma inverse, this is going to be sigma of A1, sigma of A2, up to sigma of AK sub 1, that cycle, sigma of B1, sigma of B2, up to sigma of BK sub 2, that cycle, and so forth. But sigma of A1, that's A1 prime. This is A2 prime. This is AK sub 1 prime. This is B1 prime, B2 prime, up to B sub K2 prime, and so forth. And that's tau 2. That's tau 2. So I just constructed a permutation such that when I conjugate tau 1 by sigma, I get tau 2. That's true so long as these two permutations have the same kind of cyclical decompositions.
Can you explain what the question was asking?
Yes. So another way of stating the second question was, given permutations tau 1 and tau 2 in the symmetric group Sn, prove that if tau 1 and tau 2 have, I'll just say, the same cycle structure, that means decompose into disjoint cycles of the same lengths, then tau 2 is sigma tau 1 sigma inverse for some sigma in Sn.
Thank you.
Hello? Hello?
Yes.
Can you take a look at 1.6 problem 7? I'll read it out in a second.
Okay, just 1 second. I have some clean paper here. Six. Okay.
So
Read the problem.
yeah, give me 1 second. I'm just pulling it up. So I think the problem says that, you know, increasing sequence of subgroups is finite. Let me just pull it up. I can't find it.
Prove that every strictly increasing sequence of subgroups of Z is finite.
Oh, okay, very good. So,
So I'm not sure I understand the question. So can you first explain what the question
So-
is?
you understand what it means to say that one subgroup is contained in another subgroup.
Right.
Okay. And if they are contained in but not equal, sometimes I put a little unequal sign. This means H1 is a subgroup, subset of this, or a subgroup, but they're not the same. So it's a proper subgroup.
Understood.
And maybe H2 is contained in a subgroup H3, which is different, a bigger subgroup. And maybe H4 is a subgroup which contains H3 properly. And all of these are subgroups of the integers.
So can I just
Just
ask
one
one
second.
question?
So this is an increasing sequence of subgroups of Z.
Mhm.
Okay. What is your question?
So let me give an example to see if what I understand is exactly what you're saying. So let's say you take a group Z, Z mod 2Z. And
No,
then,
we're not looking at that. We're looking at, in this problem, we're looking at Z.
okay, so let's take a look at Z. Then a subgroup would be 2Z. Then another subgroup would be 4Z. And you can construct that sequence, basically 2 power n Z. And that would be strictly contained, one will be contained within the other. Is that what you sort of like, is that a good example of what you just referred to?
Well, so what you just described is the following. We have the multiples of 2. That's a subgroup. Contains the multiples of 4 properly.
Exactly.
Contains the multiples of 8. Contains the multiples of 16, and so forth. So this is a decreasing sequence, not an increasing sequence.
Understood.
So this is an infinite decreasing sequence. So this is an example of an infinite decreasing, strictly decreasing sequence of subgroups in Z. And the problem, so in general, one has, okay, so the problem is to show that Z contains no infinite, strictly increasing sequence of subgroups.
But you could reverse the sequence, but your point is that it has to start somewhere. Let's say you start at 2 power m. In this example, then obviously because m is finite, it's going to be a finite sequence. Is that what the problem is sort of asking?
Well, I don't like the word obvious, but something like that, yes. So let's give a proof. We need to have a proof. So first of all, every subgroup of Z is of the form MZ for some positive integer M. Second, if we have one subgroup contained in the other, M1Z is contained in M2Z. What does this mean? This means that
m2 divides m1. Sorry,
M1
m1 divides m2.
M1 is times 1 is an element of MZ, M1Z, which is contained in M2Z, which means M1 is some multiple of M2,
Right.
which
Yeah,
means
that's right.
M2 divides M1. So whenever you have one subset contained in the other, M1Z contained in M2Z, M2 divides M1. And if this is a proper containment, M2 divides M1, and M2 is
Not
different
M1.
from M1. In particular, that means that M2 is smaller than M1, because M2 is a proper divisor of M1.
Right.
So if we had some sequence of subgroups increasing and so forth, we would have M1 is bigger than M2, is bigger than M3, is bigger than M4, but these are all positive integers. And there is no strictly decreasing infinite sequence of positive integers. If you have positive integers that are strictly decreasing, at some point it has to stop. So that's a proof that you cannot have an infinite increasing sequence of subgroups.
Thank you. Doesn't it also mean that, you know, M's have to be basically a power?
No, they don't have to be powers. You could have 24Z contained in 12Z, contained in 6Z. They're not powers.
Oh, sorry,
You
I
just have to
didn't mean
be-
power, but a geometric series, sort of. So
No,
in
they don't have to be a geometric
times
series
2
either.
times 2.
You could have 24Z contained in 12Z, contained in 3Z. So that's an
okay.
increasing sequence, but it's not geometric.
Understood, understood. I had one more question on permutations.
Wait, just 1 second. So
Sure.
every strictly decreasing sequence of positive integers has to be finite. That's the crux of the proof. Okay, next question.
I had another question on permutations.
Okay,
So we have looked at basically S3, the 3 permutations, and I was just looking at S4, and
Yep.
I was wondering, like, you know, let's say you take a cycle, a 4 cycle, simple 1, 2, 3, 4. If you do this first sigma square, it's still a cycle, but if you do sigma cube, then it breaks into 2 transpositions. Is that correct?
well, let's just see. If sigma is 1, 2, 3, 4, sigma squared, let's see, 1 goes to 2 goes to 3, 3 goes to 4 goes to, oops, sorry. Yeah, 1, so sigma squared,
Sorry, sigma square. Sigma square.
1 goes to 3, 3 goes to 1, that's a transposition. 2 goes to 4, goes back to 2. That's correct. And sigma cubed is, let's see, 1, 3, 2, 4 times 1, 2, 3. So 1 goes to 2, goes
1,
to
2, 3, 4,
4,
Professor.
4 goes to 2, 2 goes to 3.
Professor, sigma cube would be 1, 3, 4 at the end.
1 goes to 2, goes to 4. 4 goes to 2. 2
But doesn't
goes,
4 go to 1 first? Isn't it 1, 2, 3, 4?
oh,
Last
thank you. Yeah,
parenthesis.
thank you. Exactly. I was wondering why I was getting the wrong answer. So 1 goes to 2, goes to 4. 4 goes to 1, goes to 3. 3 goes to 4, goes to 2. 2 goes to 3, goes back to 1. Yes. So that's sigma cubed. And sigma to the 4th, 1, 4, 3, 2, 1, 2, 3, 4. 1 goes to 2, goes to 1. 2 goes to 3, goes to 2. 3 goes to 4, goes to 3. 4 goes to 1, goes to 4 is the identity. So it is true that the cycle structure is not preserved when you take powers. This is a 4 cycle, but the square is a product of 2 cycles, a product of 2 transpositions.
Okay, so no, I was just wondering if that's sort of like a general, that there is no such rule that cycle will be preserved when you take powers. So but I was wondering if that is actually true.
How do you prove that? Yeah,
How do I prove what?
that any sigma to the k is equal to the identity if they're a k, if it's a k cycle.
Oh, okay. So how do you prove that? Let me prove it first with a picture. So suppose I take a k cycle, A1, A2, A3, up to A sub k. So I always like to draw these sometimes as A1 goes to A2, goes to A3, goes to A4, goes to AK, goes back to A1. So if you iterate this, if you repeat this k times, well, I mean, actually, just look at k times. So once takes you to 2, twice takes you to 3, 3 times takes you to 4. K minus 1 times takes you to AK, and the k times takes you back to A1. You're just going around this, taking k steps around this cycle of length k. Sigma to the k is always the identity for any cycle of length k.
And that's a
One more
sufficient
question.
proof?
What?
That's a sufficient proof?
Yeah, I mean, you can say the following. For I going from 1, 2, 3 up to
K minus 1.
or even up to k, sigma of AI, you move it k sigma to the I, sorry, let me call this j. For j going from 1 up to k, what is sigma to the j of AI? Well, you move it over j steps. This is a sub I plus j, well, I should say really, but mod k. So if I plus j is more than k, because you come around. So you're just looking at this mod k. So sigma to the j of AI is a to the I plus j. So sigma to the k of AI is AI plus k, which is the same as AI. I plus k is congruent to 0, is congruent to I mod k. You're just going, like if you go once, A1 goes to A2. Twice, A1 goes to A2, goes to A3. 3 times goes to A4. K minus 1 time goes to AK. K times brings you back to A1. That's all it is.
Professor, I have one more question. When you're
Any
ready.
other questions about this before we go on? Okay, what's your question?
Same section, problem 11, which says that if G is a group and H1 and H2 are subgroups, and G is a union of H1 and H2, then G is either H1 or G is either H2.
Ah, okay, that's a very nice question. So we have a group G, subgroups H1 and H2, and we're told that G is the union of these two subgroups. So everything in G is an H1 or an H2, okay? And we want to show that one of these is in fact contained in the other. So one of them is actually the whole group, all right? So this is, let's say, a proof by contradiction. Suppose H1 is not a subgroup of H2, and also H2 is not a subgroup of H1. So what does that mean? It means, let's say this is H1, and this is H2. And if H1 is not contained in H2, there's some element X1. So there exists an X1, which is in H1, but not in H2. Otherwise, every element of H1 would be in H2, and H1 would be a subset of H2. And similarly, if H2 is not contained in H1, there's an element X2, which is in H2, but not in H1. Okay? So suppose we let Y be equal to X1 times X2. This is an element of the group, of course, because H1 and H2 are subsets of the group. This is an element of the group. If it's an element of the group and the group is H1 union H2, it has to belong to one of these sets. So if Y is in H1, then we also know that X1 inverse is in H1 because X1 is in H1. So X1 inverse Y is in H1 because H1 is closed under multiplication. But X1 inverse Y is X2. That says X2 is in H1, and that's a contradiction. That's a proof.
Thank you. Yep. A couple of clarifications. If we want to, sort of, for all these proofs, let's say some question is asking that prove this set is a group, this set is a normal subgroup. For group, if you would is proving that if X and Y belongs to that set and X inverse Y belongs to that set, then that's a group. Is that a sufficient condition?
Yes.
And for the normal subgroup, is the conjugate basically not conjugate, but whatever the X, Y, X inverse belongs to that group? That would be sufficient to prove that it's a normal subgroup?
Yes.
Okay, thank you.
Can we also do 1.4, number 6C?
If it's not too hard, we can, sure.
So for every integer k, define the 2 by 2 matrix to be sigma k equals cosine of 2 pi k over n, negative sine 2 pi k over n, sine 2 pi k over n, cosine 2 pi k over n.
Okay.
And we want to prove that I sigma squared to sigma n minus 1 is a finite abelian group of order n.
I'm sorry, so say that again, please.
Prove that the set I sigma squared all the way to sigma n minus 1 is a finite abelian group of order n.
Right, so if I called this sigma k, I probably meant the set of all sigma k's, k going from 0 up to n minus 1.
In the previous step, we showed that sigma sub k equals sigma to the power k for all integers k. And
Right,
that
so
k, yeah.
sigma 1 is cosine 2 pi over n minus sine of 2 pi over n, sine of 2 pi over n, cosine of 2 pi over n. So if you call that sigma, so sigma to the k, sigma sub k, is this sigma to the power k for all k, right? So, all right, so
Actually,
then,
can we show that also?
yes. So I'll show it in two ways, at least. So what does this mean? It's like, geometrically, if I take the unit circle and I take an angle, let's see, what should this angle be? So if you go all the way around the circle, that's 2 pi. If you divide the circle up into n pieces, each of these angles is 2 pi over n, okay? And the coordinates of this point are cosine of 2 pi over n sine of 2 pi over n. If I go another 2 pi over n, this point will have coordinates cosine of 4 pi over n sine of 4 pi over n. And in general, if I go k times around, sorry, if I go this angle k times, so this angle is 2 pi k over n, this point on the circle will have coordinates cosine 2 pi k over n sine of 2 pi k over n. So if I just look at the first column of this matrix, it's just the coordinates of this point written as a column vector. Okay. And so it's just, and I mean, geometrically, what this means is if you look at this as a matrix applied to a vector, this is just rotation. Geometrically, sigma k is rotation around the origin by an angle of 2 pi k over n radians. If you think of it like that, if you go k times around, you're back where you started. So sigma to the k is going to be the, sigma to the n is going to be the identity. But let's see. So, all right. But let's just prove this algebraically, if you like. What is sigma k times sigma L? If you multiply two of these matrices, you have cosine 2 pi k over n sine 2 pi k over n minus the sine two pi k over n cosine 2 pi k over n. That's sigma k times sigma L, which is cosine 2 pi L over n sine of 2 pi L over n minus the sine of 2 pi L over n cosine of 2 pi L over n. If you do matrix multiplication, what do you get? You get cosine 2 pi k over n cosine 2 pi L over n minus sine 2 pi k over n sine of 2 pi L over n. This coordinate is sine 2 pi k over n cosine 2 pi L over n. This plus cosine 2 pi k over n sine of 2 pi L over n. That's just the first column. And then you do the multiplication and you get your second column. But then you recognize this is the addition formula. This is the cosine of 2 pi k plus L over n sine of 2 pi k plus L over n and so on. So what this says is if you have sigma k is cosine 2 pi k over n sine 2 pi k over n minus sine 2 pi k over n cosine 2 pi k over n. If you multiply sigma k by sigma L, you get cosine of 2 pi k plus L over n sine 2 pi k plus L over n minus sine 2 pi k plus L over n cosine 2 pi k plus L over n. This is exactly sigma of k plus L. So in particular, what can we say? So sigma 2, for example, that's 1 plus 1. That's sigma of 1 times sigma of 1, which is sigma squared. And if sigma of k is equal to sigma to the power k, then sigma k plus 1 is sigma k sigma 1. That's sigma to the k times sigma. That's sigma to the k plus 1. So therefore, we have that sigma k is the kth power of sigma for all k. And oh, and we can also say, what is sigma k? Sigma k is also, well, no, we know what it is. What is sigma n? Sigma n is cosine 2 pi n over n, sine 2 pi n over n, minus sine 2 pi n over n, cosine 2 pi n over n. This is cosine 2 pi, sine 2 pi. This is 1, 0, 0, 1. That's just the identity matrix. So this says that sigma has order n. Yeah. I mean, I think that's what I was asked to prove, but let me know if there's something else that has to be proven. So this is just using the trig identities. You have to know the addition formula for the sine and the cosine. You have to know this is the cosine of the sum of the angles, and this is the sine of the sum of the angles. And when you use that, you get these identities for these matrices right away.
Do we also, once we prove it's of order n, does that already show that it's a finite abelian group?
Yes, it means it's a cyclic group. Because if you're looking, so the set of all these sigma k's, this is just the identity sigma squared up to sigma to the n minus 1. Any higher power, sigma to the n, is the identity. It just repeats. So this is a cyclic group of order n. If you take sigma to the n plus 1, that's the same as sigma.
And all cyclic groups are abelian?
Yes.
Professor,
Yeah.
have you already addressed the midterm questions?
I'm sorry. Did I address what?
The midterm sort of like answer key?
I'm not sure what you mean by address them. If you have a question about any of the problems, I'm happy to do them.
Well, I don't need you to do it. I just had a couple of clarifications that I wanted. So one of the questions, question 2, was prove that find all the integers such that 6 power n minus 1 is a prime, and the answer is none, because it's not possible, because 5 is always a factor for that.
What about 6 to the first power minus 1?
That would be 0, right? So 0 wouldn't be 0.
No. What is 6 to the power 1?
6.
And what is 6 minus 1?
5.
And is 5 a prime?
Oh, okay, yes. So yes, you're right. Sorry about that.
Okay. All right. Well, I'll be back at 4 o'clock to happy to answer more questions.
Thank you.
Okay. Bye.